My name's Ryan Tolboom. I'm working with Kwiju Gao and Parth Patel, and this is clickstream analysis using Hadoop. So the motivation for our project is really kind of getting our hands on dealing with big data. This chart's actually a little bit old now at this point, but it shows you just how much data is being collected in all these different sectors. And one of the issues we're having is you have more data than you can reasonably analyze with traditional tools. And that's kind of where MapReduce comes in. So clickstream data is a set of data that basically tells you who the referrer was and what link somebody clicked on. And it's easily pulled from logs in Nginx or Apache, and there's a lot of public data sets that we can get. So if you're a company, you probably have this data as well. We chose to use for our project the Wikipedia clickstream data, which you can get online by month. And the design of our project, our setup, was we have a Hadoop cluster running in AWS, and we used a Terraform script to basically set up a 3-node Hadoop cluster to do our work for us on medium instances. And then on that, they're running MapReduce, which has custom code that we each designed in order to perform the calculations we're looking for. And then once we've taken that large amount of data and broken it down into a smaller set that we can deal with, we did our secondary analysis, we did our visualization in Python and Excel so we can actually try to get a handle on what we're looking at. So the modules that we came up with, that we designed, were a breadcrumbs module, which determines what trails people follow as they click through Wikipedia, a top 10 module, which shows the top 10 visited pages for each different type of referrer, and you're going to see there's different types of referrers in their clickstream data, and then a type count, which is going to tell you basically how people got on different pages, what the referrer was that got them there. So some of the problems with this is that the data sets we're dealing with are huge. So you need a lot of space, and if you're pushing this out to AWS, it takes a lot of bandwidth just to transfer it over when you first set up your cluster. So if a node fails, somehow it has to be able to get at whatever chunk of the data it was working with, and that can be intensive. So in order to make our lives a little bit easier, we designed the network so that the nodes were on a internal virtual private cloud so that the data could be transferred easier between them rather than having to come from us each time over the internet. And then we used reduce functions in the MapReduce framework to take this huge amount of data and break it down into smaller, more digestible chunks. So the first module that we created was called breadcrumbs. Basically, it takes the clickstream data and it just knocks it down into, okay, based on where you're coming from, what's the most likely next place you're going to click? And it takes that, and that reduces the data set enough that you can actually make a hash of that and load it in memory on a local computer for analysis. Once you have that there, you can figure out what trails people are following as they go through. Where's the most likely place you click next? Where's the most likely place after that? So on and so forth. So doing that, we created this histogram over here on the right-hand side showing that the average trail was 4 clicks long. So typically it goes 4 clicks in before somebody either loops back or the trail ends. One interesting thing to note is that this tail extends way out over here all the way to 186. It's not on the graph, but there are some pages that have these really, really long breadcrumb trails going into them. Those types of pages are usually sequential things. So like Super Bowls, people may start at the first Super Bowl and click their way through all the Super Bowls, or the succession of presidents or popes or things like that. All right. And next I'm going to hand it off to Quijo.
Okay, so in this part, we compute the top 10 most popular links for each of the 3 types. As you can see, the first 3, the graph below, these are, the first one is external link, which is outside Wikipedia. And the second one is the internal link, which is within the Wikipedia. Third one is the other as an unknown referrer. So you can see we get all the top 10 from the different link. For example, in the external link, the first one is the main page, which is Wikipedia itself. It has totally 400 million clicks for that month, which is a very large number compares to the rest of them. As you can see, the graph below, the purple graph, which is the external link, those are the top 10 ranks. So as you can see, the first one, the main page and the hyphen minus are so large, as we cannot show the rest of it record clearly. So we cut from the 100 million number, and we get the second graph. So we can have those three different lines represent those three different types, and we can have the directly comparison. So as you can see, the link part, which is the yellow one, the orange one, it looks very flat compared to the external and the internal one. So as in those graphs, we know that the clicks of the Wikipedia main page is significantly larger than the other pages, and we also can know the people turn to search information directly from the outside link much more than search within Wikipedia or any other unknown reference, even if they're on the Wikipedia main page. So I'll pass.
Okay, so the third one that which we did was type count. So there were three different kinds of type count: external, link, and other. We shall discuss their definition later. So the implementation was done like other, that we had a mapper function which parses the clickstream data, which is in tab separated value. Now there is a reduce function which reduces the data into three referer types: external, link, and other. Now the logic to do the count was that we had a counter locally which would increment the count of each type, and at the end it would produce the output, the results. So if you see, we had a pretty huge data set. There were total like 29653,204 records. Out of all those records, the maximum number of types that was external, which was followed by link, and the other. Now the use case is that this tells us actually that how most of the clients ended up on wiki page. Now if you see the graph right hand side, it's much more generalized or in-depth. It shows not only about wiki, but it shows about Google and other websites and how it was visited from different countries, and some articles where people were reading. Next slide, please.
Okay, so for evaluation of breadcrumbs, what we noticed is that once in our cluster, once we set things up on HDFS, it was easy for the other nodes to get things from the master. So because we set up that virtual private cloud, it became easier to transfer the data internally, way easier than it was initially uploading it. All these algorithms work very well in a highly parallel environment, so they're optimal for breaking down into different smaller jobs and handing those jobs off to other nodes in the clusters. And the mapper pared down the data significantly. So you started at 1.3 gigabytes, and then it got it all the way down to 69 megabytes for the actual analysis. We did simulate a failure on the node by shutting down one of the nodes, and what happened is Yarn basically detected that the job it gave to that node never came back and ended up reassigning that task to somebody else. One cool thing about this whole system is that it allows you to provide insights that otherwise you wouldn't be able to process that size of data. So I'm going to hand it off to Quiju.
Okay, so for the top 10, as we said before, it computes the top 10 most popular links for each of the three types. It's the internal, others, and external. It runs in two parts. The first part assuming all of the referred to links aggregate by type and name, and the second part is using that data to produce the top 10 list. So the funny part is this module is the most compute intensive of the set. It's compared in map, reduce, map, and final reduce. Next page.
Okay, now the evaluation for type count. So once the data is in HDFS, that is on the master node, we can easily get the required part. This algorithm also works in a highly parallel environment, as we are just doing the count for each type from the huge data set. Now, as we discussed before, that there are three types of referer, link, external, and others. And let's see what each of these does, or they are. So link. Link basically says that if the referer and the request are both articles, and the referer links the request. Basically, someone is on an article, and then they click on it, and they end on wiki page. Now the other one is external. So basically, someone directly goes to the wiki page. And lastly is other. Other is quite similar to link. So like the referer and the request are both articles, but there is no link in that particular article. Basically, the client searches for that particular keyword on the Wikipedia, or they spoof, or they basically try to recreate that kind of referer. Next slide, please. Conclusion. So based on the programs or the parts that we did for this project, we have two different kinds of conclusion. On the left hand side, we have the three things that we did: breadcrumb, top 10, and type count. On the right hand side is our experience with this MapReduce and Hadoop. So let's first go with how the three parts ended up working for us. So the first conclusion that was derived from the breadcrumb was that on an average, breadcrumb trail is 4 pages long, which is longer for pages in a sequence. Second, for top 10, the main Wikipedia page gets a huge amount of external clicks, and that is in the third order of magnitude, which is pretty large number compared to the other pages. And the link type is relatively flat across its top 10. And most clients visit a Wikipedia page using a link found in the article in comparison to other types such as external and other. So when we say link, that means the user or the client was already on some kind of article and they clicked on it and they ended up on wiki page. Now we shall talk about that how was our experience with Hadoop and what kind of things that we saw for the MapReduce. Type of analysis is not computationally intensive, but it does require copying a large amount of data, which means that the data set that we had, copying it on the HDFS took the most of our time, or copying it on the node rather than doing the computation. Second part is most expensive part of node failure was making the data available to new node, which is pretty straightforward. That in order to have the MapReduce work seamless, we need to make the nodes available for other mapper and reducer functions or workers to take care of the work. The Hadoop framework seamlessly handles failure. And the last point is performance is dependent on the data locality. So if you want to achieve a higher performance within one node, it is highly evident that the node that is running the function has the data on the same node rather than trying to look up on another. That's all from our side. Thank you.